Ken here, and welcome to the Metropolis. On today's video, we're going to be talking about how physicists have created a holographic wormhole using a quantum computer. Pretty cool stuff, all of it sounding very science fiction-esque, but evidently that is where we are at now. So we have this great article pulled up from quantummagazine.org. Let's dive in and see what this is all about. Alright, so physicists create a holographic wormhole using a quantum computer. The unprecedented experiment explores the possibility that space-time somehow emerges from quantum information, even as the work's interpretation remains disputed. There's a nice little graphic, I guess. I don't know if this is actually accurate. I think this is more aesthetic representation or an exaggeration of things, but I guess it's supposed to represent the quantum computer and then the actual holographic wormhole, quote-unquote. It says researchers were able to send a signal through the open wormhole, though it's not clear in what sense the wormhole can be said to exist. Interesting. So, physicists have purportedly created the first ever wormhole, a kind of tunnel theorized in 1935 by Albert Einstein and Nathan Rosen that leads from one place to another by passing into an extra dimension of space. The wormhole emerged like a hologram out of quantum bits of information, or qubits, stored in tiny superconducting circuits. By manipulating the qubits, the physicists then sent information through the wormhole, they reported today in the journal Nature. The team, led by Maria, I'm going to butcher that last name, led by Maria of the California Institute of Technology, implemented the novel wormhole teleportation protocol using Google's quantum computer, a device called a Sycamore housed at the Google Quantum AI in Santa Barbara, California. With this first-of-its-kind quantum gravity experiment on the chip, as Maria described it, she and her team beat a competing group of physicists who aimed to do wormhole teleportation with IBM and Quantum's quantum computer. I don't know, that might be a proprietary computer, a quantum computer that IBM has. I know a number of these companies are doing this sort of research. Let's check it out. Okay, so this, I guess, is just a scholarly article noting their intent to try and accomplish the same thing, or a similar thing. Interesting. Okay, so, but they beat them to the punch, so to speak, and then when Maria saw the key signature indicating that qubits were passing through the wormhole, she said, "I was shaken." When she saw the key signature indicating that qubits were passing... That's a pretty beautiful line right there. And it's pretty fundamental to a lot of interstellar travel, science fiction, futuristic hypotheses, and lore. Wormholes, as mentioned in the article, have been predicted by Einstein, who also predicted a number of other things that came to light. So, not terribly surprising that this is now something that we're actually manufacturing. I'm curious what a holographic wormhole is. I don't know if that's different than just like a regular wormhole, or if that's how they're accessing the properties of it. And it seems so far that they've said they've sent the information one way. I'm not sure if they know where it has been sent. But this is a pretty beautiful line right here, and it's kind of nice to know with all the craziness going on in the world currently that right now this person, Maria, which I'll just take a stab at it, Sparapula, like, I'm sorry I'm butchering your name. I'm sure you'll never see this, but I mean no offense. But when they saw the key signature indicating the qubits were passing through the wormhole, they were shaken, and I can only imagine, because the implications there are something similar to, I'd say almost like splitting the atom or seeing a little bit behind the veil of what's possible. So very cool stuff. The article goes on to say, the experiment can be seen as evidence for the holographic principle, a sweeping hypothesis about how two pillars of fundamental physics, quantum mechanics, and general relativity fit together. And if you're unfamiliar, it's a classic thing in physics where you have, I believe it's Newtonian physics, which was general relativity. I believe I might be screwing that up, which is very embarrassing, but I do know you have these two competing core bedrocks of physics, general relativity and quantum mechanics, and they have never been able to be married. There's never been able to be a grand unified theory, if you will, and that's been kind of like the big goal that a lot of people have been going for to some things. That's what string theory was aspiring to do for a while. That's what a number of theories of everything have aspired to do. And so this might be this holographic principle and its hypothesis looks to solve at least aspects, or maybe entirely, how quantum mechanics and general relativity, fit together. So if that's the case, then that's also, a very profound thing. Physicists have, even though, like I said at the beginning of this, some of this is still disputed, still exciting stuff. Physicists have strived since the 1930s to reconcile these disjointed theories. Yeah, so exactly what I was just saying. One, a rule book for atoms and subatomic particles. The other, Einstein's description of how matter and energy warp the space-time fabric generating gravity. The holographic principle, ascendant since the 1990s, posits a mathematical equivalence or duality between the two frameworks. So a mathematical equivalence or duality. Interesting. So it seems like two different sides of the same coin, perhaps through different lenses. It says the bendy space-time continuum described by general relativity is really a quantum system of particles in disguise. Space-time and gravity emerge from quantum effects much as 3D hologram projects out of a 2D pattern. Space-time and gravity emerge from quantum effects much as a 3D hologram projects out of a 2D pattern. Interesting. And there is this whole... I'm somewhat familiar with the concept of the holographic universe. I don't know if that's different than the holographic principle. Holographic universe is also a great book that I, read a good amount of, and the thesis in it is that the whole universe is holographic, essentially, that there is like the all in the small, or as above so below, the patterns in nature that are just such that you could have all of the information in the universe somehow fit into the tiniest bit. Not even talking about the Big Bang, not even talking about billions of years ago when everything was crunched and then spat out. More so that information, like all information, is accessible at all times, and that everything works on a holographic basis. Like, as far as I understand holograms, you could have a bit of film, like you could have a picture. This is a very stupid layman's interpretation of it, or an explanation of it, but you could have a picture, like a holographic picture. We'll just say a holographic picture, for lack of a better term, and it has like a sofa on it or something. And then you cut that picture, and then inside the little cut that you did of that picture is still the full picture. Like, you don't lose any information, basically. So that's what I understand about the holographic universe. And I'm curious, the holographic principle seems to be related. They might just be different words for the same thing. Let's check out this video here. Wormholes were first envisioned almost a century ago, but it would take a number of theoretical leaps and a crazy, quote-unquote, team of experimentalists to build one on a quantum computer. Pretty wild. And it's really cool to see what quantum computers are doing now, because they've been a technology out for quite some time, and they've yet to produce really groundbreaking stuff that I've seen. Not that they're not working on it, but this is the first thing that I personally can call in recent memory being really excited about, other than, like, I don't know, really strong encryption. So it goes on to say, indeed, the new experiment confirms that quantum effects of the type that we can control in a quantum computer can give rise to a phenomenon that we expect to see in relativity, a wormhole. The evolving systems of qubits in the Sycamore chip, quote, has this really cool alternative description, end quote, said John Preskill, a theoretical physicist at Caltech who was not involved in the experiment. You can think of the system in a very different language as being gravitational. To be clear, unlike an ordinary hologram, the wormhole isn't something that we can see. While it can be considered, quote, a filament of real spacetime, unquote, according to co-author Daniel Jafferis of Harvard University, lead developer of the wormhole teleportation protocol, it's not part of the same reality that we and the Sycamore computer inhabit. The holographic principle says that the two realities, the one with the wormhole and the one with the qubits, are alternate versions of the same physics. But how to conceptualize this kind of duality remains mysterious. Opinions will differ about the fundamental implications of the result. Crucially, the holographic wormhole in the experiment consists of a different kind of space-time than the space-time of our own universe. That is trippy as hell. Crucially, the holographic wormhole in the experiment consists of a different kind of space-time than the space-time of our own universe. So yeah, again, that just makes me think of the two sides of the same coin, but we never see the other side. So we're sending information, evidently, to a different configuration of this sort of space-time that we yet to have perceptual access to. Could be like right on, likely I imagine is right on top of us. It's the same thing, but just like we can only see certain colors in the color spectrum, we don't have direct access to perceiving this as of yet. But evidently the information was sent, so it's a matter of where this information was sent, as far as I'm understanding this. It's debatable whether the experiment, the article goes on to say, furthers the hypothesis that the space-time we inhabit is also holographic, patterned by quantum bits. I think it's true that the gravity in our universe is emergent from some quantum bits, in the same way that this little baby one-dimensional wormhole is emergent from the Sycamore chip, Jafar said. Of course, we don't know that for sure. We're trying to understand it. Some background on Einstein. They theorized this before they had the technology to test stuff out like this out. Einstein and Rosen speculated that Schwarzschild's math might be a way to plug elementary particles into general relativity. To make the picture work, they snipped the singularity out of his equations, swapping in new variables that replaced the sharp point with an extra-dimensional tube sliding to another part of space-time. It's insane for me to like think about how they envision this or theorize this without the kind of modeling and technology we have now. It's very impressive. Einstein and Rosen argued, and I've heard the term Rosen bridge, and I don't know if that was just in some Star Trek that I saw once, but I'm aware of Einstein and I'm aware of Rosen, but this Rosen bridge that I've heard of, I wonder if that has similarities. Oh, obviously. Rosen argued wrongly but presciently, like he was prophetic, that these bridges or wormholes might represent particles. Interesting. Ironically, in striving to link wormholes and particles, the duo did not consider the strange particle phenomenon that they had identified 2 months earlier with Podolsky in the EPR paper Quantum Entanglement, which is another trippy phenomenon. Entanglement arises when two particles interact. According to the quantum rules, particles can have multiple possible states at once. This means an interaction between particles has multiple possible outcomes depending on which state each particle is in to begin with. So if you're not familiar with the double slit experiment or the concept of quantum entanglement in general, they pretty much cover it here, and essentially saying matter has this interesting feature where it's affected by the observer. It's in a number of different states simultaneously, but it is not isolated into a single state until it's observed, as far as I understand it. Always, though, their resulting status will be linked. How particle A ends up depends on how particle B turns out. After such an interaction, the particles have shared formula that specifies the various combined states they might be in. This shocking consequence, which caused the EPR authors to doubt quantum theory, is quote-unquote spooky action at a distance, as Einstein put it. Measuring particle A, which picks out one reality among its possibilities, instantly decides the corresponding state of B, no matter how far away B is. So, basically extending upon what I just said, whereas measuring or observing this particle, which is in a bunch of different states at once, thus dictates the actual state it will be in. Not dictates with choice, it almost seems like random, but of the different states, it doesn't choose a state, I guess it doesn't allocate a state until you observe it or measure it or look at it. And there are entangled corresponding particles, and it doesn't matter how far away they are, I guess they will be linked, and you'll be able to measure them in some sort of corresponding aspect. And that's what came up with this quote-unquote spooky action at a distance. Again, peeling back the layers of reality. But this has been a known concept for a while. The spooky action, or a known theory, or whatever. I believe it's been measured, so it's not really a theory at this point, but it's been a rub of this whole peeling behind the curtain of reality thing. Entanglement has shot up in perceived importance since physicists discovered it in the 1990s, that it allows new kinds of computations. Entangling two qubits, quantum objects like particles that exist in two possible states, as 0 and 1, yields four possible states with different likelihoods: 0 and 0, 0 and 1, 1 and 0, and 1 and 1. 3 qubits make 8 simultaneous possibilities, and so on. So you see how the math would stack there, obviously. The power of the quantum computer grows exponentially with each additional entangled qubit. Cleverly orchestrate the entanglement, and you can cancel out all combinations of zeros and ones except the sequence that gives the answer to a calculation. Prototype quantum computers made of a few dozen qubits have materialized in the last couple of years, led by Google's 54-qubit Sycamore machine. Meanwhile, quantum gravity researchers have fixated on quantum entanglement for another reason, as a possible source code of the space-time hologram. All right, so this goes into some pretty neat depth. I'm not going to read every bit of it. It is pretty extensive about how we got here to this point. But the fact that they are able to, as far as I understand it, send information. Perhaps they do have more information about where it's going, but as I've seen it thus far, it looks like they've just been sending it and then there's some dispute about where it's going. Let's read through it, make sure I'm not getting that wrong. It's like according to this graphic, it looks like they do know where it went. They might be sending single particles through wormholes. Okay. So I believe they come to a conclusion on this. Sorry, it's the first time I'm seeing this article. Probably just edit this out. Anyway. So the article goes on. As the theoretical work was developing, Maria, an accomplished experimental particle physicist who was involved in the 2012 discovery of the Higgs boson, which I believe is also referred to as the God particle, because it's something they had been looking for quite some time. Yes. So she's already very accomplished and in the deepest layers of this, was thinking about how to use nascent quantum computers to do holographic quantum gravity experiments. In 2018, she persuaded Jafaris to join her growing team along with researchers at Google Quantum AI, keepers of the Sycamore device. Which I have to say, the more I'm reading this, the more the Sycamore device sounds like some crazy, not necessarily malevolent machine, but at least something that is cracking a code, and those with access to the Sycamore device, let's just hope they're on the benevolent side of things. And thus far, this seems very benevolent, very just inquisitive. But the Sycamore device does have a cool little ring to it. To run Jafaris and Gow's wormhole teleportation protocol on the state-of-the-art, but still small and error-prone quantum computer, Maria's team had to greatly simplify the protocol. A full SYK model consists of practically infinitely many particles coupled to one another with random strengths as four-way interactions occur throughout. This is not feasible to calculate. Even using all 50-odd available qubits would have required hundreds of thousands of circuit operations. The researchers set out to create a holographic wormhole with just 7 qubits and hundreds of operations. To do this, they had to sparsify the 7-particle SYK model, encoding only the strongest four-way interactions and eliding the rest. I'm not even going to lie, I've never seen this word. Omitting. Leaving out the rest while retaining the model's holographic properties. So to do this, they had to sparsify the 7-particle SYK model, encoding only the strongest four-way interactions and leaving out the rest while retaining the model's holographic properties. That took a couple of years to figure out a clever way to do, Maria said. And this looks to be heard. Pretty cool on the cutting edge of this amazing stuff. Props to you. Appreciate what you're doing. One secret to success was Zlokapa, a Wayfish Orchestra kid who had joined Maria's research group as a Caltech undergrad. I gotta say, I feel terrible about butchering all these names, and I apologize. A gifted programmer Zlokapa mapped the particle interactions of the SYK model onto the connections between neurons of a neural network and trained the system to delete as many network connections as possible while preserving a key wormhole signature. The procedure reduced the number of four-way interactions from hundreds down to 5. That's amazing, and an amazing use of a neural network. Very, very cool. Very cool. With the team starting programming Sycamore's qubits. With that, the team started programming Sycamore's qubits. 7 qubits encode 14 matter particles, 7 each in the left and the right, SYK systems, where every particle on the left is entangled with 1 on the right. An 8th qubit in some probabilistic combination of states, 0 and 1, is then swapped with one of the particles from the left SYK model. That qubit's possible states quickly get tangled up with the states of the other particles on the left, spreading its information evenly among like a drop of ink in water. This is holographically dual to the qubit entering the left mouth of a one-dimensional wormhole in ADS space. Then comes the big rotation of all qubits, dual to a pulse of negative energy. Then comes the big rotation of all qubits, dual to a pulse of negative energy coursing through the wormhole. The rotation causes the injected qubit to transfer to the particles of the right-hand SYK model. Then the information unspreads, Preskill said, like chaos run backwards, and refocuses at the site of a single particle on the right, the entangled partner of the left-hand particle that was swapped out. Then the qubit states are all measured, tallying zeros and ones over many experimental runs and comparing these statistics to the prepared state of the injected qubits reveals whether qubits are teleporting over. So they definitely are. This is a functional wormhole. That's crazy. That is absolutely insane. A functional wormhole teleporting bits of matter. That is mind-blowing. The researchers look for a peak in the data that represents a difference between two cases. If they see a peak, it means qubit rotations that are dual to negative energy pulses are allowing qubits to teleport, whereas rotations in the opposite direction, which are dual to pulses of normal positive energy, don't let qubits through. Instead, they cause the wormhole to close. So obviously, they're figuring out kind of a system, as they analyze the results of these qubits and I guess which direction they've rotated. Goes on to say, late one night in January, after 2 years of gradual improvements and noise reduction efforts, Zlokapa, and I believe this is the individual right here, the programming genius, ran the finished protocol on Sycamore remotely from his childhood bedroom in the San Francisco Bay Area, where he was spending winter break after a semester of grad school. How quaint and poetic. Definitely love that. I say that with no condescension. That's amazing and beautiful. The peak appeared on his computer screen and kept getting sharper and sharper, he said. I was sending screenshots of the peak to Maria and getting very excited, writing, I think we see a wormhole now. The peak was the first sign that you could see gravity on a quantum computer. Maria says she could hardly believe the clean, pronounced peak she was seeing. It was very similar to when I saw the first data for the Higgs discovery, she said. Not because I didn't expect it, but it came too much in my face. Surprisingly, despite the skeletal simplicity of their wormhole, the researchers detected a second signature of wormhole dynamics, a delicate pattern in the way information spread and unspread among the qubits known as size winding. They hadn't trained their neural network to preserve this signal as it sparsified the SYK model, so the fact that the size winding shows up anyway is an experimental discovery about holography. Very cool. We didn't amend anything about the size winding property, but we found out that it just popped out, Jafar said. This confirmed the robustness of the holographic duality, he said. Make one property appear, then you'll get the rest. Then you get all the rest, which is a kind of evidence that this gravitational picture is the correct one. So it finishes with the meaning of the wormhole. Jafaris, who never expected to be part of a wormhole experiment or any other, thinks one of the most important takeaways is that the experiment, what it says about quantum mechanics. Quantum phenomena, like entanglement, are normally opaque and abstract. We don't know, for instance, how a measurement of particle A determines particle B's state from afar. But in the new experiment, an ineffable quantum phenomenon, information teleporting between particles, has tangible interpretation as a particle receiving a kick of energy and moving at a calculable speed from A to B. Quote, there seems to be a nice story from the point of view of the qubit. It moves casually, said Jafaris. Maybe a quantum process like teleportation always feels like gravitational to the qubit. If something like that could come out of this experiment, other related experiments, that will definitely tell us something deep about our universe, and I imagine have an insane amount of implications. So again, to avoid reading the entirety of this very long but informative and amazing article, I'm stoked. That's pretty profound in its nature, and the findings and the implications and the work they're doing is just pretty cool. Seems very under the radar, just like, you know, the Higgs. They do this work and then you find these like little blips, but when they continue graduating from just simple particles onto more advanced things, I'm excited to see what they do with this this wormhole tech, which is essentially what they're developing with the Sycamore device and this wormhole tech they are creating. So let me know in the comments if you're excited about this, if you are afraid it's going to tear the entire space-time reality and create a mist type situation a la Stephen King, or you know, if you just want to use it to get around, which I don't know how fast that will be coming up, but you know, Moore's law being what it is, who knows. But yeah, just exciting stuff. So I'll see you next time, and thanks for watching. Cheers. Bye.